In this presentation, we will talk about Q value of nuclear reaction. Consider this nuclear reaction. Capital X is the target, small x is the incoming particle. The incoming particle, after interacting with the target, produces a daughter nucleus and an outgoing particle with the emission of some amount of energy. The energy Q is harvested from the kinetic energy difference. The value of Q equal to final kinetic energy minus initial kinetic energy. Initially the target is at rest. The projected particle kinetic energy is Ex because of its motion. After completion of the nuclear reaction, an outgoing particle and a daughter nucleus are generated. The kinetic energy of the daughter nucleus is Ey and the kinetic energy of the outgoing particle is E suffix small y. The final kinetic energy is equal to Ey plus Ey. Initial kinetic energy is Ex. The difference between these two will provide the value of Q. The Q value of a nuclear reaction is the difference between the kinetic energies of the products and that of the incident particle. Therefore, the change in the kinetic energy in a nuclear reaction is the nuclear disintegration energy. According to conservation of mass and energy, the energy of small x is the summation of its kinetic energy and rest mass energy. The energy of capital X is its rest mass energy alone because it is at rest. There is no talk about kinetic energy. The energy of the daughter nucleus is its kinetic energy and rest mass energy. The energy of the outgoing particle Y is its kinetic energy and its rest mass energy. Now the new equation of the form 2 is generated. If you get the value of Q, that is equal to Ey plus Ey minus Ex, then the rest of the terms are aligned to the right hand side and we can get the equation of this form. Now we may point out that the right hand side is rest mass energy term, left hand side is difference in kinetic energies, that is Q. Q is equal to the change in the total rest mass multiplied by C square. We may also point out that Q is the change in the total rest mass. Here, if Q is positive, the reaction is exergic, that means some amount of energy is released. If Q is negative, the reaction is endogic. For positive Q, the value of Ex should be lesser than Ey plus Ey, and the quantity Mx plus Mx should be greater than that of My plus Mi. If Q is negative, then Ey plus Ey should be lesser than Ex and the quantity Mx plus M suffix small x should be lesser than M capital Y plus M small y. Now we have to find out the Q value of alpha decay. Consider an alpha decay process. Here XZA is an element. If it emits an alpha particle, the atomic number is reduced by 2 units, whereas the mass number is decreased by 4 units. In addition to that, some amount of energy is generated. This is called as disintegration energy. To calculate the disintegration energy, we have to assume the mass of the daughter nucleus as M suffix D and the mass of the alpha particle by M suffix alpha. Velocity of the daughter nucleus is V suffix D, whereas the velocity of the alpha particle is V suffix alpha. Then the momentum of the alpha particle and the momentum of the daughter nucleus are almost equal in magnitude but opposite in direction. Therefore, we can write mdvd equal to m alpha v alpha. We know that Q is equal to final kinetic energy minus initial kinetic energy. The initial kinetic energy is 0 because the target is at rest. Final kinetic energy means the kinetic energy of the daughter nucleus plus the kinetic energy of the alpha particle. Half mv square is formula for kinetic energy. Then half into m suffix d, mass of the daughter nucleus, into vd is the velocity of the daughter nucleus. This is the kinetic energy of the alpha particle. From this relation mdvd equal to m alpha v alpha, instead of vd we can write m alpha v alpha by md. Say m alpha v alpha by md. vd square, therefore entire is squared, plus half m alpha v alpha square. Take the term of m alpha v alpha square as a common term. Here we have taken out m alpha v alpha square, so remaining one m alpha is present. This is m alpha. This md by md square is md. Therefore, half m alpha v alpha square into m alpha divided by md plus 1. Here half m alpha v alpha square is k alpha, kinetic energy of the alpha particle. Therefore, Q equal to k alpha into m alpha by md plus 1. Replace m alpha by 4 unit, md by means of a minus 4. Now substitute these values. Q equal to k alpha, instead of m alpha we have to substitute 4 because mass number of alpha particle is 4. Here this md is a minus 4 because in this reaction x is at a, say x is at a, after emitting an alpha particle we can get x is z minus 2 a minus 4 plus an alpha particle. See here, once the alpha particle is emitted, the daughter nucleus mass is a minus 4. So a minus 4. This one is present as such. Cross multiply, we can get k alpha into 4 plus a minus 4. That is equal to a divided by a minus 4. Here the quantity a divided by a minus 4 is almost equal to 1 because if you think about uranium 238. Uranium 238 minus 4 is 234. Here A is 238. Almost there is no change in the quantity A divided by A minus 4. That is almost equal to 1. Therefore, the value of Q is almost equal to K alpha, which means that the alpha particle carries away most of the disintegration energy. This is the conclusion we arrived from the Q value of an alpha particle.